So myself, Dr. Keshavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So my main topic is experimental technique. Today I am going to discuss about the experimental technique of the laser glass spectroscopy. So last and previous session we discussed about the synthesis and the preparation of glasses. That is importance of glass, material selection, classification of glasses by preparation methods, preparation of glasses by melt quenching technique, different lanthanum 3+ dope laser glasses, physical properties of glasses. These topics are we discussed in the last session. Today I am going to discuss about the experimental techniques. The outline of the topic is electron paramagnetic resonance studies, that is EPR studies, electron paramagnetic resonance studies. Second one is optical absorption spectrometer. Next, third one is excitation, emission and decay time measurements. Next, fourth one is X-ray diffraction, XRD profile measurements. Next, last one is Raman spectrometer. These are we are going to study the experimental techniques we are studying for the glass systems. First one is electron paramagnetic resonance. EPR studies. That is, in EPR studies, we are going to study the unpaired electrons, how many electrons are there in the outermost orbital electron configuration. That we are going to study in the structural properties of the EPR studies. So there are several commercial EPR spectrometer operating at different frequencies, fabricated and supplied by Varian. That is, company name is Varian from USA. Next, Geol is Japan, and the other one is Broker is Germany. So usually they are using most of the laboratory. They are using GL and Broker. These are the famous instruments from the EPR studies. GL company and Broker. These are the Japan and Germany companies. They are used a lot of research laboratories. They are using for EPR study purpose. They are using this kind of instrument, GL instrument or Broker instrument companies. This spectrometer operates at a fixed microwave frequency and EPR spectral scanning by a linear variation of magnetic field. So here studying the magnetic field, linear magnetic field variation whenever applying the microwave frequency. We are applying the operating at a microwave frequency, that X band, Y band, P band, different kind of bands is there. That band frequency we are using. At the same time, the variation of magnetic field. So in order to observe well-resolved EPR spectra, the instrument was operated under optimum conditions of microwave power, modulation, amplitude, spectrometer gain, filter time constant, scan range, and scan time. These are the very important parameters while measuring the EPR spectra analysis. So that is the very important is microwave power. How much power you are going to use, modulation, amplitude, spectrometer gain, filter time constant, scan range, how much scan we are going to analyze the spectrum, and the scan time also. These are the important parameters while measuring the EPR spectra analysis. The work described in this dissertation was carried out on a GL FEX ESR spectrometer. The electron spin resonance and electron paramagnetic resonance both are the similar only. The ESR spectrometer operating at X band frequency. This is very important. In this presentation, we are use the X band ESR spectrometer, that is having 100 kHz field modulation to obtain first derivative EPR spectrum. First derivative ESR spectrum or EPR spectrum, we are going to do the X band frequency. So we are using the X band frequency, at the same time 100 kHz field modulation obtain first derivative EPR spectrum. These are the electron paramagnetic resonance studies. Next, this is the black diagram for the Geol EPR spectrometer. Model number is JES FE1X. This is the Japan company Geol instrument. That is the Geol EPR spectrometer. So this here, see this is the black diagram for the EPR spectrometer. See here, recorder, filter circuit, amplifier, next oscilloscope, and see voltage. These are the black inside the EPR spectrometer. There are the different various kind of tools will be there. That is operators. This is the linear and field sweep unit. Next 100 kHz and say here derivative switch controls and AFC circuit and gun oscillator power supply. This is first starting from the gun oscillator power supply to microwave unit. These are the prominent essential parts in the EPR spectrum. Gun oscillator power supply, microwave unit, From microwave unit to pre-amplifier, then comes to the different kind of amplifiers and filter circuits, the recorder, and again comes to the here modulation power supply. We have to adjust the modulation power supply while using the um, microwave frequency. We can modulate the power supply, how much we can require to use. So here is the sample cavity here. This is the electromagnetic current we can using here. This from X band EPR spectrometer, we can microwave frequency we are applying from the to the sample. It will reflect and it will comes to the detector. It will apply the detector by using the different kind of parts. We can use the power supply and the linear field modulation chip and the Hall element excitation power supply. These are going to measure, and after sample cavity too, it will come to the detector. So in detector, we can observe the sample output of the signal. That signal we can come into the computer. That is connected with computer. We can see the what is the EPR signal. Finally, output of the sample we can measure by using the computer. This is the black diagram for the electron parameter resonance spectrometer. Next, this is the how it looks. This black diagram is inside the parts inside this one. So this is the here. See the this different modulation. The magnetic field here. This is the magnetic field you are applying. This is the oscilloscope. This is the oscilloscope. The magnetic field, how much magnetic field you are applying. This is the detector. We can see the here spectra reading. How spectra looks like. So here this parameter, these knobs are we can adjust the modulation, voltage, power supply. These are this is the photograph of GL-FE1X ESR spectrometer. This spectrometer operates 100 volt to 260 volt amperes. Its magnetic control unit controls the magnetic field over a range of 0 to 600 millitesla. We are a magnetic field. We can vary the from 0 to 600 millitesla. We can vary the magnetic field while applying the microwave frequency. The 100 kilohertz and 80 hertz of modulation unit amplifier in the EPR signal. The oscilloscope spectra 133 millimeter persistence provides a facility for mode check and observation of EPR signal. The DYT type recorder records the EPR signal and chart with a 250 millimeter to 360 millimeter. We can record the chart also, we can record, and otherwise you can connect it with the computer. We can record the EPR signal by using the GOL ESR spectrometer. In this spectrometer, we are going to study the how structure will be there. That is a site symmetry. We can going to study in the EPR spectra size symmetry. So if outer boat electronic aggressive Mn2 plus iron 3 plus chromium 3, usually they are measuring the tangent metal ions in the EPR spectrometer. So in outermost orbital, each electron state will be there. The 2 plus state or 3 plus state or 1 plus state. So that structure property we can study in the by using the EPR spectrometer. So in this, how it will work? The gun diode oscillator is generates microwave over a frequency range of 8.8 GHz to 9.6 GHz. This is the band of X band. This is in our spectroscopy in EPR spectrometer is the X band. So X band range is the 8.8 GHz to 9.6 GHz. That is X band. At power variable from 0.1 micron watts to 200 milliwatts. The oscillator frequency is mechanically varied by varying the cavity resonant frequency. It varies the different kind of frequencies, that is cavity resonant frequency. The EPN spectra can be recorded either by first or second differential curve of the absorption signal. So we can get the first derivative of absorption curve, we can get in the curve only we can calculate the EPR signals. See, the instrument has a high magnetic field homogeneity and stability. It has a very high sensitivity, that is very important. It is having the high sensitivity, that is 2 into 10 power of 10 to 3 into 10 power 10 springs for gas. That is a very important. Sensitivity is a very highly accuracy. High resolution is 1 into 10 power of minus 5. And the frequency stability is 1 into 10 power of minus 6. That is the frequency stability. Whenever applying the high power, that stability will be very, very more important while regarding the neutron parameter resonance studies. The high to cavity and hot carrier diode enable to accomplish high sensitivity in EPR measurements. The horizontal axis is expandable from 360 millimeter to 1080 millimeter while recording the signal with the recorder. Whenever recording the signal at that time, you can see the horizontal axis expandable from 360 millimeter to 1080 millimeter while recording the EPR signal. The EPR spectra at a different temperature can be recorded by using a JES VT3. We can study the room temperature EPR signal or ESR signal. At the same time, low temperature also we can study by using the dual ESR spectrometer. That variable temperature controls capable of regulation the temperature from 523 K to 103 K. Temperature we can measure the low temperature. The EPR signal also we can measure by using the dual ESR spectrometer. A temperature stability of plus or minus 1 K was easily obtained by waiting for half an hour before recording the spectrum. Before recording the spectrum, we can wait the half an hour because it will variation temperature variations will be stability will be plus or minus 1 K only, 1 Kelvin only. Whenever time minus 1 minus plus 1 it will be fluctuation there. That stability will be more or less 1 Kelvin only. So by using the alternate parameter measurement studies, we can study the at room temperature ESR signal. At the same time, low temperature US signal also we can study by used to attach with that EPR spectrometer attached with JES VT3A. Another instrument we can connect with ESR signal. We can measure the variable temperature ESR spectra also. So that is we can temperature will be varying is from 523 Kelvin to 103 Kelvin. We can use to measure the ESR signal at low temperature also by using the dual ESR spectrometer. So this is next second one is the optical absorption spectrometer. So the optical absorption spectrometer is lanthanum doped glasses were recorded using Perkin-Elmer lambda 950 UV visible NIR spectrometer. This is Perkin-Elmer suppliers. That is the model number is lambda 950 UV visible NIR spectrometer. We can measure UV visible, ultraviolet to visible near infrared region. So we can use the spectrometer range from 200 nanometer to 3000 nanometer. We can observe the optical absorption spectrometer by using the Perkin-Elmer lambda spectrometer. The photograph of the instrument and its black diagram are shown in figure 1 and figure 2. The technical specification of the spectrometer also shown in table. This is the optical absorption spectrometer of the Perkin-Elmer lambda 950 UV visible NIR spectrometer. This is the model name. Perkin-Elmer lambda 950 UV visible NIR spectrometer. This is the optical absorption spectrometer. We can observe the absorption as well as transmittance. Also, we can measure by using the optical absorption spectrometer. Next, this is the black diagram for Perkin-Elmer lambda 950 UV visible NIR spectrometer. See, this is here the inside the optical absorption spectrometer. There is a two monochromators. This is one monochromator 1, monochromator 2. Because we can measure the UV visible at the same time NIR region also. So we need high regions. That means spectral region from 200 nanometer to 3000 nanometers. So in that purpose we need two monochromators. That is UV visible NIR. So you have to measure. One time you can use the monochromator 1 and some other measurements we can use the monochromator 2. So these are the different kind of M1, M2. These are different kind of mirrors. So inside the optical absorption spectrometer there are different kind of mirrors they are using. Because we have to tune the laser beam from the one lens to mirror and mirror to means. So we can focus the laser beam through the monochromator and comes to the sample compartment and comes to the detector compartment. So in that way we can measure the optical absorption spectrometer by using the Perkin-Elmer lambda UV visible spectrometer. So this is two radiation source, namely deuterium lamp. Here they are using two kind of lamps they are using for the measure the UV visible absorption spectrometer. First one is deuterium lamp DL. The other one is halogen lamp. So they are different lamps using to measure the all spectral regions from 200 nanometer to 3000 nanometers. Cover the working wavelength range from the spectrometer for operation in the near infrared NIR region and visible region range. Source mirror M1 reflects the radiation from the halogen lamp onto mirror M2. At the same time, it blocks the radiation from the deuterium lamp for operation in the ultraviolet region. So whenever you are measuring the ultraviolet radiation, it will stop the deuterium lamp. Otherwise, sometimes halogen lamp. So these are the both mutually it will work on the deuterium lamp as well as halogen lamps to measure the complete spectral ranges. So mirror M1 is raised to permit radiation from the monochromator sleeving. So radiation from the respective source lamp is reflected from mirror M2 via mirror M3 through an optical filter and the filter wheel FW assembled to mirror M4. The filter wheel is driven by a stepping motor to be synchronization of the monochromator. So in this black diagram, this M3, M4, these mirrors can be stabilized the each and every focusing the light beams. So depending on the wavelength being produced, an appropriate optical filter is located in the beam path to free filter the radiation before it enters into the monochromator. So whenever it enters to the light focus on the monochromator, we have to some filters they are using to tune the laser beam. So radiation before it enters into the monochromator, next filter changes automatically during monochromator sleeving. Whenever changing the filters, we can tune the filters. So this is the table shows the certain technical specifications of Perkingham lambda 950 view visible NIR spectrometer. This is the item and specification. First principle. What is the main principle of the measure the optical absorption spectrum? This is a dual beam because we are using the two beam, double beam spectrometer. There is a double monochromator. There is a monochromator 1 and monochromator 2. Next, ratio recording UV visible NIR spectrometer with microcomputer electronics and are controlled by the personal computer. So these are the main principle of the specification in the optical observation spectrometer. Second one is optical system. All reflecting optical systems are silicon dioxide coated holographic grating monochromator with 1440 lines per mm, U visible blazed at 240 nanometer and 360 lines per millimeter, NIR blazed at 1100 nanometer with little little throw mounting. These are the optical systems of the optical observation spectrum. What kind of detectors using here? So U visible photo multiplier R6872 photo multiplier we are using by regarding the detecting the UV visible spectra. If you are measuring the NIR region, will code of the PBS detector using. So in UV visible, they are using photo multiplier tube. That is number is R6872. If you are measuring NIR at time, then lead sulfide detector are using to detect the absorption signals. And source. Next one is source is pre-aligned tungsten, halogen, and deuterium lamps are using. This is the main source. We are monochromator. We are using the main source of the optical absorption spectrometer is halogen, tungsten halogen lamp, and as well as deuterium lamp for UV visible. At the same time, NIR regions. The wavelength range from 175 nanometer to 3300 nanometer. We are going to measure the optical absorption spectroscopy. We can vary the absorption wavelength from 175 nanometer to 3300 nanometer, we can measure the optical absorption spectrometer. So UV visible resolution, that is UV visible resolution, what is the fluctuation when I am measuring the wavelength range? At that time, what is the resolution of the UV visible range is are greater than equal to 0.05 nanometer. That is very less. That means we can highly resolution will be good. Next, NI resolution is are less than or equal to 0.20 nanometers. So these are the important specification for the Perkingham lambda UV visible NIR spectrometer. Next, coming to the photo multiplier. We are using two type of detectors are using. One is halogen lamp, other one is a deuterium lamp. So photo multiplier PMT detector is used in UV visible range, while lead sulfide PBS detector is used in the NIR spectral range. Detector changes is automatic during monochromator sleeving. At the cell plan, each radiation beam is approximately 12 millimeter height. So each and light radiation beam approximately 12 millimeter height. The width of the radiation beams is dependent on the slit width. That is mainly dependent on the slit width. At a slit width of 5 nanometer, each radiation slit width is 5 nanometer beam is approximately 4.5 millimeter wide. That beam wide is approximately 4.5 millimeter wide. They permit minimum sample volumes to be measured in a microcell. The height of the radiation beam must be reduced in active cell area. A common beam mask CBM, a common beam mask is mounted between the slit assembly SA and mirror M7. This mask restricts the cross section of the both sample beam and the reference beam in the respective cell area, because this is a double beam spectrometer. That is a one beam you can go to sample and other one is a reference beam. So both beam coming together, then output will be you are getting from the monochromator to the detector. The spectrophotometer scans from higher to lower wavelength. There is an optional depolarization filter DPF. That means depolarizing filter DPF accessories when can be swing into the beam. We can measure the higher wavelength to lower wavelength, lower wavelength to higher. Normally we are using lower wavelength to higher wavelength. Sometimes we are using, there is an optional depolarization filter DPF. We can use the higher wavelength to lower wavelength region. We can scan the optical lens spectrometer by using the UV visible Flickr Link spectrometer. So third one is the excitation, emission and decay time measurements. So after revolutionary class studies, we can use the luminescence studies. That is luminescence studies, we can measure excitation, emission and decay time means time measurements also we can measure it by using the Jobin ion fluorolog 3 spectrophlorimeter. This is the fluorescence spectrometer. We can measure the excitation, emission at the same time, lifetime measurements, the decay time measurements also we can measure it by using the Jobin ion fluorolog 3 spectrophlorimeter. So in this, the excitation, emission and decay measurements of the classes to be studied were recorded on a Jobin ion fluorolog 3 spectrophlorimeter with a xenon arc lamp. Here we are using the xenon arc lamp at 450 watt as an excitation source. Here we are using the excitation source as a xenon arc lamp that having the 450 watts of the power supply we can give. We study the state of the xenon flash lamp is used to study the lifetime measurements. We are using xenon flash lamp. While measuring the excitation emission, we are using the xenon arc lamp. These are the very important parameter in the excitation, emission, decay time measurements. The optical layout, also a photographic of spectrometer are shown in the figure 3 and 4. This is the instrument of the Jobin ion fluorolog 3 spectrophlorimeter. We are going to use for the excitation, emission, decay time measurement purpose. We are using this fluorolog spectrometer. Next, what is the outline or black diagram of the excitation, emission and decay time measurements? Here, this is the source. This is double grating excitation spectrometer. This is a PMT photomultiplier tube. This is T-bug sample compartment model. This is the double grating emission spectrometer. We can, by using this black diagram, we can this source. So in xenon flash lamp, arc lamp we are using, and this is the different kind of mirrors we are inside the instrument. We are using different kind of mirrors. This comes source to coming to the through mirror and the lens, different kind of lens we are using, and we are measuring the through PMT detector. The PMT detector we are measuring, and we are collecting the signal from double grating emission spectrometer. That way we are measuring the excitation spectrum, emission spectrum, as well as decay time measurements, also the lifetime measurements. So a source is xenon arc lamp. For radiation produces photons, and beam of light could be filtered by an excitation spectrometer that allows a single wavelength of light to reach the sample, and in the sample compartment, the sample responds to the incoming radiation. It responds to the incoming radiation. The resulting radiation is filtered by an emission spectrometer that feeds the signal to a photomultiplier detector. So comes from the signal, we can detect by using the photomultiplier detector, we can measure the emission signals. The fluorescence decay curves that gives the information about the lifetime of excited states of lanthanum 3+ ions in a host composition can be obtained by controlling the emission wavelength upon the given excitation wavelength. This is mainly depend on the excitation wavelength and emission wavelength. If you want to measure the fluorescence lifetime measurements for the different kind of lanthanide ions, we can choose the what kind of wavelength we can use for excitation parting purpose. At the same time, in which emission we need to measure the lifetime measurements. In different kind of emission wavelength will be there. So in our requirement, we can choose the emission wavelength. At the same time, pumping wavelength also we can tune the wavelength as per your requirement. That is, we can measure the lifetime measurements also by using the. So in only one instance of fluorolux spectrometer, we can measure the three type of measurements. That is, one is excitation spectrum we can measure. At the same time, emission we can measure. Lifetime measurements also we can measure. So in this instrument, we can measure the three type of spectral measurements we can do by using the fluorolux spectrometer. So the lifetime of the excitation level can be simply determined by finding the first e-folding times of the decay curves. By using the lifetime measurement signal, we can first e-folding times of the decay curve, we can calculate the lifetime measurements of each and every lanthanide ion lifetime. We can measure by using the fluorolux spectrophotometer. Next, coming to the fourth one is X-ray diffraction. XRD means X-ray diffraction. So most of the metals and alloys are crystalline in nature. Hence, one of the most useful calibration technique is XRD. If you want to measure the structural studies, is a glassy surface or crystalline material, we can measure the first structural study by using the XRD instrument. We can measure the different kind of metals or alloys for the crystal nature. We can measure the crystal nature by using the XRD instrument, that is X-ray diffraction spectrometer. So XRD is based on the Bragg's law. It is mainly works on the Bragg's law. This is the main principle of the XRD is Bragg's law. That is 2D sin theta equal to n lambda. N అనేది integer number, 1 or 2 first order, second or third order. Lambda is the wavelength. D is the interplanar distance between the two planes. That is D. Sin theta is the diffraction angle. That is 2D sin theta equal to n lambda. This is Bragg's law. By using the Bragg's law, we can calculate the XRD profile of XRD curves. The intensity of the diffracted X-rays is measured as a function of diffracted angle and the specimen orientation. So we can measure the intensity of the diffracted X-rays is measured as a function of diffracted angle and the specimen orientation. This diffracted pattern is used to identify the specimen's crystalline phase and to measure its structural properties. Structural properties we can measure by using the XRD. The diffraction peaks are accurately measured with XRD, which gives information about homogeneous and inhomogeneous strengths. So we can measure the diffraction peaks by calculating the XRD peaks. We can get the information about the homogeneous as well as inhomogeneous strengths we can measure by using the XRD spectrum. Next, X-ray diffraction, that is XRD. If there is no inhomogeneous strains, the crystalline size D can be estimated from the peak width with the Serrer's formula. That we are going to Bragg's law. It will be working principle of the XRD is Bragg's law. By using the Bragg's law, we can measure what is the crystal size D value. Crystal size also we can measure by using the XRD profile or XRD curve. There is a formula, Serrer formula. Based on the Serrer formula, we can measure the crystal size of the material. That is D equal K lambda by B cos theta. B cos theta. That is in XRD, where lambda is the wavelength, B is the full width of maximum. This is the full width of maximum of the diffraction peak. Theta B is the diffracted angle. Theta B is the diffracted angle, and K is the Serrer constant. So K is the Serrer constant. That value is 0.91. That is a constant value whenever measuring the XRD profile. So this XRD is useful for the following applications. So different kind of applications we can use the XRD. The study of D-spacing. We can use to study the interplanar distance D-spacing we can measure by using the XRD. Next one, study of mixtures. Different kind of mixtures we can measure by using the XRD. Study of crystal symmetry also we can measure by using the XRD. Study of alloys also you can measure it by using the XRD. Next, stress determination in metals also we can measure. And also finally, determination of particle size by using the Serrer formula. We can measure the particle size, how much is the crystalline size, how much is there, we can measure. So in this diagram shows this is the Bragg's law. Here incident angle is fall under the sample at diffracted angle. This is theta. This is the crystal planes here. These are the atoms inside the crystal. So here this is one plane, this other plane. These two planes in between distance is the D. That is the interplanar distance is D. So here from here fall onto the sample. Here theta. Let's come inside. This gap should be 2D sin theta. That is the constructive interference when n lambda equal to 2D sin theta by using the Bragg's law. This is D sin theta. So one more sin theta. That is 2D sin theta. D sin theta plus D sin theta, 2D sin theta. that we are going to get here. By using the Bragg's law, we can calculate the XRD structure. Just coming to this XRD instrument. See here, this is the XRD instrument. There is a X-ray source. Next, primary X-ray optics. Next, gonimeter. Next, detector. Sample holder here. Next, here, diffracted beam collimator. So by using this here, X-ray source fall on the sample. Next, it will diffracted beam comes from this measure the X-ray detector from here. So that is X-ray. Direct X-ray beam will be produced like this. So by using this mechanism, by using the Bragg's law, we can measure the XRD profile. So in the case of if we have a glass sample, we can measure the XRD by using the X-ray diffraction spectrometer. We can measure the powder X-ray diffraction pattern of the typical glass structure will be XRD profile will be looks like this. So we can get the broad signals. But we cannot get in the soft. That means if you are getting soft curves means that shows the crystalline nature. But in this profile shows the broad peaks. That means it's exhibit the glassy sample completely glassy nature. So by using this XRD profile, we can measure this is a glassy nature or crystalline nature. We can confirm it by measuring the X-ray diffraction. Next, last one is a Raman spectrometer. The Raman spectrometer is a remarkably useful calibration technique for structural analysis. So Raman spectrometer we are going to use for the structural analysis purpose. We are using the Raman spectrometer. Raman spectroscopy involves the measurement of Raman intensity as a function of wave number of the inelastic light scattering that results from the excitation of vibrations in molecular and crystalline materials. Molecular can crystalline materials, so we can measure the Raman spectrometer. For structural analysis purpose, we can measure the Raman spectrometer. The excitation source in a single line of a continuous gas laser. We can use argon ion laser, helium ion laser. This kind of gas laser we are using for the measure the Raman spectroscopy, which permits the optical microscopes for measurement of sample down to few micrometers. It will focus on the sample down to few micrometer. It will scan the sample and gives the Raman spectrum analysis. It is sensitive to molecular and crystal structure. Applications include chemical fingerprinting, examination of single grains in ceramics and rocks, single crystal measurements, identification of compounds in bubbles and liquid inclusions, investigations of structure and strange states in the polycrystalline ceramics, glasses, fibers, gels, thin and thick, different kind of systems we can study the for Raman spectrometer. We can study the ceramics, glasses, fibers, gels, thins and thick films. Thin films we can measure the by using the Raman spectrometer. It will scan the down to the sample to down to depth is a few micrometers depth we can scan and will give the measurements of the Raman analysis. Next is the Raman spectrometer. How schematic diagram for the Raman spectrometer. So here using laser required, that is a gas laser. We can see different kind of wavelength. We can tune the, if you are using the argon ion laser, we can tune the different kind of wavelengths. If helium laser also, we can tune the wavelengths. That is laser. We can using shutter, mirror and beam splitter. We can split the beam splitter. What it will do means it will split the beams in two directions. One direction goes to Raman microscopy, other direction goes to lens. So these are the Raman spectrometer. From laser source, it exhibits the laser beam. It comes to shutter to mirror. From the mirror, it comes to beam splitter. It will split beam from to the Raman microscope. Some beam will comes to lens to filter. And here Raman microscopy comes to sample. Here focus on the sample. Here keep on the sample holder. There is photometer. This is computer. So this Raman microscopy used to scan the sample, and again it gives the signal to input to the lens and filter. And coming to the lens, you will go to CCD. Grating using the grating, you are detecting the signal and it will transfer into the computer. The data transfer to the control system. So by using this CCD through, we can measure the Raman spectral analysis. So here inside the Raman spectrometer, what kind of mechanism it can work? So here applying the laser beam to the sample. So here scattering effect. This is scattering. This Stokes and anti-Stokes. It will exhibit the different kind of scattering. So first one is mu naught minus mu. This is Stokes and anti-Stokes. Mu naught plus mu. This is anti-Stokes, Stokes. So anti-Stokes is represented as the Raman scattering. So from some other scattering also there, that is a Rayleigh scattering. This is not useful for the measure the Raman spectrometer. So it will be eliminated, and it comes to the Stokes and anti-Stokes. We can measure by using the Stokes and anti-Stokes scatterings. We can measure the Raman scattering. By using the Raman scattering, we can analyze the structural analysis of the different kind of samples. We can measure the glass sample or crystalline sample or films, thin films or plastic materials. We can measure different kind of polymers also. We can measure the by using the Raman spectrometer. It gives the structural analysis of the glass materials or ceramics or any different kind of materials. So finally, we can detect the by using the computer. We can get the this kind of data. That is Raman spectral data. So the basic principle in this technique is that when electromagnetic radiation is scattered by a molecule, most of the photons scatters elastically with the same frequency and wavelength as that of the incident photon. So incident photon, that is having the same frequency and wavelength. However, a small fraction of the electromagnetic radiation is also scattered inelastically. As a result, the scattering electromagnetic radiation possesses different frequencies in comparison to the incident radiation. This phenomena is known as Raman effect. This phenomena, scattering of photons, that phenomena is known as Raman effect. In Raman spectroscopy, the sample is irradiated by intense laser beam. So here applying the laser source in the UV visible region, and the scattering light is approximately uniform in all directions and is observed in the direction perpendicular to the incident beam. We will measure the direction perpendicular to the incident beam. So in this way, Raman analysis, we can measure the samples. So in this process, the scattering electromagnetic radiation consists of two types. One is Rayleigh scattering, which is strong and has the same frequency as that of the incident beam. And the other one is called Raman scattering. So we are in the Raman spectrometer, we are observing the Stokes and anti-Stokes. That is the Raman scattering. It's a very weak, that is a 10 power minus 5 of the incident beam, and its frequency is mu naught plus or minus mu m. Mu m is the vibrational frequency of a molecule. So Raman spectroscopy mainly used to study the phonon bands. So what is the phonon of the glassy sample or ceramic sample? Any sample, we can measure the vibrational frequency. We can measure by using the scattering, Raman scattering. We can measure the Raman scattering. We can measure the vibrational frequency of the different kind of samples. We can measure the Raman spectroscopy. So these are the reference gathered from the experimental techniques. So this is the 6 references: the ESR spectrometer, optical observing UV visible spectrometer, and fluorescence plasma spectrometer. And these are the different references gathered from the experimental technique of the EPR electroparameter studies, and optical observation studies, and Raman studies, and the excitation, emission, and lifetime measurement studies, and exciting properties. These are the references for the experimental technique. So, thank you. To be continued in the next session. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.